Good morning, everyone. I'm very excited to join you remotely today from Waterloo, Canada, to present to you a very holistic overview about the RF in the Wi-Fi, and also present a very interesting use case that we have been working on at Solace Power. And if you have any questions, I will leave some time at the end to have some question and answers. So I'm looking forward to it. Just to know each other, I've put in a small introduction. So I've worked in the wireless industry for over a decade, and it has been I've been very fortunate to work in a home networking area to develop many interesting products at Microsoft, Liberty Global, and Corpo. And over the years, I've learned that the RF part it is quite interesting and also challenging, and that is the foundation for your whole communication system, which I would like to discuss a bit today. Also, I've been part of a Wi-Fi Alliance before, and I would highly recommend everyone to look at the device metrics test plan, which was released, I think, a couple of years ago, which was one of the first industry's Wi-Fi performance test plan made by Wi-Fi Alliance. So presently, I'm working as an integration architect at Solace Power. It is a company based in Newfoundland in Canada, and they are developing a very interesting wireless power systems, the wireless power transfer system, which we'll touch at the end of the presentation. So at the end, you will see how the integration of Wi-Fi 7 with the wireless power transfer is unlocking potentials, like unlocking the fixed wireless access capacity. And we have seen we can double the FWA capacity with this technology. Okay, well, let's dive into the about the RF and Wi-Fi. So I will start with the whole Wi-Fi 7 feature list. So Wi-Fi 7 has a very good refresh rate. Wi-Fi is updated every couple of years, and if you look at Wi-Fi 7, which most of the industry is developing products now. So here are some of the key features based on what it is optimizing. So I have broadly put it in peak throughput, power savings, client density, spectral efficiency, low latency, and range. Right. So features like 4K QAM, 320 megahertz, which I think is one of the most key features of Wi-Fi 7, is driving the peak throughput. And on the other side, innovations in the RF, which is with digital pre-distortion with the front end, is driving the power consumption down or meeting those high QAM rates. Also, there are a lot of low latency features, which is mostly on the Mac layer, on the PHY layer and the Mac layer. But you will see that if you have a good RF, those features also work well, right? So I will not go into a lot of details about each of this, but the focus of the presentation would be really the RF, that would be the channel bandwidth and the MCS rates, and a bit on spectral efficiency. So if you look at a system Wi-Fi system architecture, so that's something you will find in a Wi-Fi CPE, like a Wi-Fi gateway. You have a main SoC which handles the Ethernet and maybe handles the fiber XGS PON or GPON. And then you have the Wi-Fi SoC, which integrates the baseband with RF. And then you have the whole RF front-end chain, which consists of filters, RF front-end, diplexers, matching, and antennas. Right? So just to give you an idea, today you can just go buy an off-the-shelf Wi-Fi 7 reference design, and you will get a good idea about all these blocks that connects the antenna to the wireless SoC, and which I've marked here, and you can take a look later when you have the slide. Okay. So one of the key, in this presentation, I will focus on the RF front end, on filters, and on diplexers, because those were the thing which I had to optimize for developing a POC later, which we'll discuss. So if you look at the RF front end, It is basically a discrete component. You can see example here from Corvo, which is a 2.4 gigahertz RF front end, and it integrates a lot of components in it. It integrates a PA, integrates a low noise amplifier, it integrates switches, it integrates a coupler, it integrates a BAW filter sometimes. But the most important thing to look at is on the transmit power is the job of the RF front end is to give you the low EVM that you require, which is the error vector magnitude to achieve the 4K QAM. And that is always a challenge. So whenever there's a Wi-Fi standard refresh, currently in Wi-Fi 7, you are at 4096 QAM. That means your EVM has to be like below -40, right? So what that means is that your PA has to be very linear. So your AM, PM, which is amplitude modulation, phase modulation, and AM distortion. So that basically the distortion. So if you input a signal to your PA, the output is distorted, the phase is distorted, the amplitude is distorted, and you cannot tolerate a lot of noise and a lot of distortion in your to achieve a 4K QAM. So that is the job that your front end does to provide you excellent linear PA. On the other hand, if you look at the receiver sensitivity on the receiver side, the low noise amplifiers have an excellent noise figure. So they are sometimes around 1.4 dB or below. And that basically compensates for a high noise figure integrated LNA in a Wi-Fi chip. So what usually happens is your Wi-Fi silicon LNA is not made for excellent noise performance because it's limited by current amount of power it draws. So if you look at the cascade system, the first LNA in the chain determines the total noise figure. So that's very critical. And the third one I would like to cover is heat dissipation. So that is one of the most critical aspects we have found by developing CPEs. And digital pre-distortion is basically saving you at least 0.5 watts per chain with Wi-Fi 7 technology. So here again, I've given this slide for you to take a look when you have some more time, and look at the key features that you should look at when you are selecting a RF front end. So we talked about noise figure, EVM. You should look at the spectral mask that it produces, especially for NCS0, which is the beacons. You should look at the time domain performance by the burst length for 4 millisecond packet, which is like a beacon, or a short packet, which is an aggregated MPDOs. The 1 dB compression point, right? All these parameters impact your RF performance and help you to select a good RF front end. Next, we'll touch on the spectrum and the filtering. So you must be aware that with Wi-Fi 6 and Wi-Fi 7, now you can operate in 3 bands. You have the 2.4, you have the 5 low and high, and the 6 low in India now. In US and FCC, you still have the whole 1.2 gigahertz and 6 gigahertz. So to develop a dual band, tri-band, or quad band architecture, a lot of filtering is used to split the bands. I have shown some examples here with this red blocks where you definitely split the 2.4, you split the 5, you split the 6, sometimes you split the 5 into half, sometimes you split the 6 into half. And it all depends on how many concurrent bands you want to support on the router. Usually it's dual band. You will see a lot of dual band. On high end, you will see tri-band, and that would be 2.4, 5, and 6. These filters play a very critical role also for coexistence with LTE, like band 40 cellular band on 2.4, or meeting the band edge for FCC, which is minus 41.2 dBm per hertz. So any noise that you produce above that is not allowed in 2.4. Another important characteristic of this filter is that it avoids spectral regrowth of your transmit signal. And also, it limits the noise on the receiver. So especially for concurrent use cases when 6 gigahertz is transmitting and 5 gigahertz is receiving, you need those filters to have low noise in your receiver. So all these things would impact your multi-link operation, or also the fact to achieve like higher peak data rates in your Wi-Fi system. Here is it like two popular filters that are used in the market, which is SAW and BAW. The SAW is surface acoustic wave and BAW is bulk acoustic wave. So for lower frequencies up to for 2.4 gigahertz, SAW filters are very popular, and they are both are fundamentally based on piezoelectric material, where an electric signal is converted into acoustic signal, and that acoustic mechanical vibration basically resonates at 2.4, 5, or 6 gigahertz, and it gives you excellent rejection. So you are talking about rejections up to 60 dB with a very, very sharp roll off. So the if you look at the Q factor here, it's above 1,000. So you can imagine how sharp those filters are, right? So this is a marvel of a technology that has been developed by some semiconductor companies. They provide very low insertion loss, high rejection, and they're excellent for Wi-Fi systems. So I will leave this slide again for you to take a look. There's a lot of details which you can go into, and we can, of course, discuss this later. Here I would like to give you the very good exemplary of what a BAW filter does. So if you look at here, there is a BAW filter on the 5 gigahertz Uni 3 spectrum, right? And if you suppose do not have any filtering, because of spectral regrowth, when I talked about the PA being non-linear, and it is basically spreading your Wi-Fi skirts, you basically have a lot of noise that is coming in the Wi-Fi 6 gigahertz channels. That is just because of the OFDM nature of Wi-Fi and the high PA/RR ratio. So especially for low MCS rates, you start to see a skirt going pretty broad. But suppose now you put a filter on the 5 gigahertz band, now suddenly your rejection, you mitigate that spectral regrowth substantially by 60 dB, up to 60 dB based on the filter you choose. And that means that you are able to now concurrently operate like transmit on 5 and also receive on 6. So that's, I think, really key when you want to do some design a tri-band or dual band system. Now we'll move to diplexers, which I think is also pretty interesting because it helps you to save cost and space to integrate multiple antennas. If you look at a typical tri-band system, if you have 3 antennas on 2.4, 4 on 5, 4 antennas on 5, and another 4 on 6, so you're talking about around 11 or 12 antennas total in your box. And if you want to integrate those 12 antennas, it's quite a challenge to have the isolation, orientation. It's costly. So I like diplexers in the sense because it inherently provides you 30 dB isolation between the 2.4 and 5 gigahertz example here. So if you look at any typical Wi-Fi router today, diplexers are very common for 2.4 and 5. It provides you that inherent isolation. It eliminates basically additional antenna, but it also comes with some cost that you have insertion loss of around 2 to 3 dB. So basically you cannot transmit at the maximum EIRP. And also your spatial positioning of antennas is limited. So sometimes you don't get a complete omnidirectional pattern if you combine the antennas. So I think those are some system trade-offs that you would have to make when you want to design your Wi-Fi system. Okay, I'll now come to the use case I was talking about. So at Solace, we are basically we just developed the wireless power transfer system, right? And we were looking at applications of our technology, and we found out that if you look at the fixed wireless access devices today, which are usually indoors, there is a very high penalty of RF signal propagation through windows. especially in North America and Europe, where you have double pane, single coated or double pane, double coated, metal coated windows. You can have attenuation up to 30 dB on the FR1 band, so sub 6 gigahertz band. And we have done some measurement with our open source router, and we saw that you have a penalty of 19 dB SNR if you move your 5G receiver from outdoors to indoors. So to solve this problem, what we did was to basically move the 5G receiver outdoors and also power that receiver and the Wi-Fi AP wirelessly from indoors. So that's the system that you see here. It's called 2-box. And what I would like to discuss is the RF challenge, how we solve the RF challenges with some open source off-the-shelf devices. This is a bit more, I will not go into details, but this is how the power transfer system looks like. It can do 30 watts magnetic coupling, and it can handle misalignment. So that's how the system looks like. This is the interesting part where this is a development for last 6 months where we wanted to develop a demonstrator, and we found a MediaTek has MT7988A Wi-Fi 7 reference platform. I think it's called Banana Pi. So that's the only Wi-Fi 7 reference platform we could find off the shelf. So we hooked up 5G module, and we hooked up antennas to it, and then we actually designed this whole 3D casing with it. And what we found out was that it's not trivial to just put these things together and it works, because the most critical part was thermals. To meet the thermal challenges, we had to do a lot of innovation in airflow and how to extract the heat from the devices. So coming back to RF, we solved some of the RF challenges here by putting some reflectors between the antennas that face the window and the antennas which face the 5G gateway, 5G base station, and also the antennas which face the home. So we did not have a lot of control on the filters that were used, but we had control on how we can position the antennas and how we can isolate them. And that's what we did. And I can show you some results. Also, something in our control because we had the open WRD firmware was to play with transmit power. And this is something you'll find interesting, that it is not always necessary that if you transmit at high power that you have high throughput. So what you see here is that because the window link here is very short, it's like 3 centimeters, and you have a 30 dB attenuation, you're not limited by link budget, but you are limited by large signal. So if you transmit, so 0 is basically very high power, and we started to reduce the power by 2 dB. So what we saw is that when we do a throughput test, if you set maximum power, you have low throughput, and that is because your LNA is getting into a compression, right, and it's creating noise. So this was pretty interesting that we reached a maximum throughput when we reduced the power to 11 dBm for the window link, right? And I think that's something to note, that for optimized system, you need to work in the linear region for your LNAs. So this is just to show you that by using the 4K QAM and 320 megahertz feature of Wi-Fi 7, we were able to achieve up to 3.5 gig throughput on that short window link, right? I mean, this is expected for a Wi-Fi 7. I would expect a bit more with 3x3, but it's all, again, it comes down to your RF integration, like how you position the antennas, what is the isolation of your antenna, do you have good MIMO uncorrelated medium or not. But this was quite a significant result with an open source firmware from an open source hardware. Next, I would like to share some, there is a test result. So we had a problem that we did not have a test house to do some repeated tests. So we basically used a reference house, which was quite good because it had brick walls, it had insulation in the walls, and so it had also those double pane, single coated and double coated glasses. So the penetration of RF of 5G was pretty poor inside the home. And we used this to basically test our 2-box system that I showed. at these 4 locations. And what we saw is that by putting those reflectors on the antennas, the red ones that you see here, so these ones are the 5G antennas in the outdoor unit. These one are the Wi-Fi antennas for the through glass link. And in the indoor unit, again, you have the Wi-Fi antennas for the through glass and for the home networking. You can see that you have 25% increase in downlink just by improving the isolation between antennas, right? And you could test it if you have a very decent calibrated place to measure TCP throughput. Yeah. And this is another slide on like end-to-end throughput where we talked about the BAW filter coexistence. And here you can see that end-to-end where you had I had a 6 gigahertz link for the through glass, and I had 5 gigahertz for the client link. And I think the Banana Pi uses ceramic filters. They're not BAW filters. So we could actually achieve pure full coexistence because we were limited by 1 gig Ethernet speed, and we could achieve 1 gig in downlink in a couple of one and couple of locations. So to conclude, we just touched on some of the RF aspects, and this is a prototype. And when you want to certify your product, you have to go through a lot of RF aspects, right? Very few of them are basically designed like which you don't have to worry about, like because that's part of the silicon, like LO leakage or carrier frequency offset. But the rest, the EIRP, radiated power, PIS, antenna isolation, all the job of the system architect and the team who's designing the Wi-Fi system. Because as we saw, when you put in an RF front end, when you put in an antenna, you put in a filter, you put in a diplexer, you impact the EIRP and transmit power, right? So you want to measure it. You want to be sure that it is not adding a lot of loss. And all of these features would impact your Wi-Fi 7 performance. So overall, there is a very interesting interplay of amplitude, time, spatial, and frequency domain when it comes to looking at all these RF features, which you need to balance and test to have a very good Wi-Fi performance system. So thank you. That's all I have today, and happy to answer any questions you have.